Well, I think we're just about there. Welcome back, everyone. So this is probably the hardest class, I think, to attend in all of fall semester, the day right before a really long break. So appreciate you all making it in today. That's not easy to do. And same for folks who came in through Zoom today as well. Today, we're not going to go too crazy and try to run right to the last minute, but we're trying to get into a good position so that when we come back from the break, we'll only have not too many topics to get through and plenty of time for review. So my goal is to finish 6.4. This one's a pretty short section. We're just looking at graphing mainly, a couple related topics on domains. And then we'll try to make some headway to 6.5, but I'm not going to try to get too far on that. Just enough so that we're familiar with what's about to happen when we come back from the break. Other announcements I have so far are that, well, we definitely have a break coming up. And over that break, there's going to be no classes, no office hours. I think the campus itself is officially just locked up that whole week. But I'll still be available for questions. So if you have questions as usual, don't hesitate to email. Even over the break, I'll be happy to help out. I won't be at my email throughout the whole day, but I'll usually be able to check that email early in the morning and things like that. Well, any questions so far, folks, about the announcements or otherwise? Okay, other things to mention is definitely the exam 3 we just had on Tuesday's class. I'm about halfway through grading everyone's set so far, so sorry didn't quite get it on time on this one. That's really unfortunate because of the break. I'll be sitting on those exams for quite a while. If you're dying to know what your grade is, you can definitely check it on Moodle. If you want to know more information, just send me an email at any time. You can say, hey, Mike, is it possible I could get my exam back? And it definitely is possible. I'll scan it and send it back to you. So don't hesitate to email if you're really, really curious about your exam. That's a long wait to get returned until Tuesday of December, it looks like. Well, any questions, folks, about exams or otherwise? Okay, let's go back to our actual Moodle website. So when we come back from the break, on this week, we'll be taking a look at section 6.5, section 6.6. And when we come back on this week here, we'll be finishing off the last section 6.7, then reviewing for the final exam. And that means there's going to be a lot more information that's posted here. Over the Thanksgiving break, I'm going to add a little bit more information. The final exam is going to allow us all to have a note card with anything you'd like on it to support you on getting through the final exam. Also, the math department has printed out, I think, 1 page of notes front and back of notes that you're able to freely use on the real final exam, which will be included on the exam itself. So the final exam is not as bad as exam 1, 2, and 3 in that sense, at least. So that's pretty much where we're at, where we're going so far. We really only have about 2 weeks and a day to get through, so we're just about there. Any questions at all then, before we go back to our section here? Okay, let's give it a start. In 6.4, we're looking at graphs of logarithmic functions, which is kind of strange because we've done graphs of those. We did them in section 6.3 up here, for example. But I guess this is our official section. So here it is. Let's give it a try. We're going to graph this function right here. G of x equals log base 5 of x. There's a lot of ways to graph these things. You could get, say, a table of points, x, y coordinates, and you could pick up a calculator and just calculate your y coordinate for any x value. That's not a bad approach to take, and it will work on Alex. But I'm going to take a slightly different approach on this, just to show how to do it by hand. Then when we do this one here, we'll show how to do it on the calculator as well. So if you see something like this and Alex asks you to graph it, it shouldn't have to be as torturous as their discussion page right before that topic. You can actually use your calculator on this and just graph it in a more straightforward way. But think of this as our warm-up here. We've duplicated the notes from section 6.3. When you look at the function g of x equals log base 5 of x, what we're doing is obtaining a function inverse to this. If that was 5 to the power of x, its inverse is log base b of x. So probably the easiest way to graph this, if we're doing it by hand, is just take this equation here and replace y with g of x. So here it is, y equals g of x. Next line, we can substitute in and put in the actual function. G of x is log base 5 of x. Then the immediate next step to take is, let's convert this to exponential form. To get it in exponential form, we need to observe the base as 5. I'll write that base of 5 over here on the left. Once we have that, we take the x that's right here, and it's now the input to the exponential function. It's essentially going right there where it says b to the x. So let's just throw x here. Once we have x placed, we take the output of the logarithm, and it's going to go, oh, hang on. I think I got a little bit mixed up on my approach. When I wrote this out, it might have been helpful if I kept my 5 over here. That way I'm not going to get mixed up on either side of the equation. If 5 is here, it's a little bit more easy, at least for me, to see y comes over here. And the actual input is the output. I could tell something was wrong when I was trying to say the output is the input. It didn't quite work out unless we have y right exactly here. So that's our new function, x equals 5 to the power y. If we write this out, now it's really fast to get x values and y values all together. So let's go y equals 5 to the power of x, or excuse me, 5 to the power of y. Sorry, I'm getting a little confused on my table here. Let me put a y first and a 5 to the power of y here at the output. We should have drank a little bit more coffee here, but this ought to work out for us to this stage. Probably a good spot to pause though. So pretty much all I did to start, wrote down y equals g of x, throw in the g of x function, and then after getting mixed up a little bit, keep your base 5 here just to make it a little bit more clear. So now x becomes the output, y becomes the input. And so now we're just putting in values right here in this table. Now it's easier to choose y values. That's why I placed y first. If you say y is -1, we'll just go right up here. Now it's 5 to the power of -1. And that exponent law says we just get 1/5 out of that. Plug in a 0 for y, and you'll get x is 5 to the power of 0. Now it's a +1, and probably next easiest value would be a +1 itself. We have 5 power 1, which equals 5. And we could keep on going, but at 2, we're up to 25. We're pretty much leaving the scale of the graph at that point. So now we have a bunch of coordinates, a y and an x coordinate. And if we graph our logarithm, we can make it look something about like this. All these values are pretty much just going to be in quadrants 1, quadrant 4. There's going to be a horizontal asymptote that goes through like this, right through the y-axis. So there it is at x equals 0. That's what we did all of us on our quiz. If we have a logarithmic function like this one, our vertical asymptote goes through the y-axis. Then on this line, it's a little bit mixed up because I have an x coordinate here and a y coordinate here. So if we'd like, we could correct these order pairs and just say, as an x and y table, it's 1/5 for x, -1 for y. Then it'll be 1 for x, 0 for y. Then finally, we have a 5 for x and a 1 for y. Lots of switchings with x's and y's, but that's because we're dealing with the inverse function, which will literally switch your input x and your output y. And we're seeing it on the table here. Now finally, let's maybe put a value of 1, 2, 3, 4, 5. So we've got at least the right extent going vertically. At 1, it has a value of -1. Excuse me, at 1/5, we're at -1. At 1, we're at 0, so right around here. And finally, at 5, we take a value of 1. So this would be my not so bad, but definitely a by-hand sketch of the graph. It's attracted to this vertical asymptote right here, so it has to get really close as we approach in this direction. I'll just let the arrow point down there to say it's going towards that vertical asymptote. But as we sketch to the right, it increases in an extremely slow way. Because it's the inverse of the exponential that increases rapidly, this one ought to increase very slowly, like we're seeing here. We did it, folks. That's our entire graph to this thing. Any questions or comments to get that graph produced here? Okay. Again, you could have really just put in interesting values right inside the function. But if we're thinking of what we did in section 6.3, converting it to exponential form is not a bad strategy. Then after doing this, I think the bigger takeaway of why you would want to graph these logarithmic functions, it's about the domains. And domains suddenly become really, really critical with what we're going to do in the next sections because we'll be doing equation solving. And if we come up with a value not in a domain, it's not a solution to the equation we're trying to solve. So just for a quick related topic, well, I guess they did ask domain and range. Let's say for the domain of G, on the graph, we can definitely see it's from 0 to infinity with a parenthesis. Well, let's suppose what you would do if you didn't see the graph. You would grab the function g of x right here, equals log base 5 of x. And if this is all we're looking at, we didn't have a graph at all to help us out. To get the domain, this is exactly what we would do. Take our, maybe green is a good choice here, whatever's inside here, and solve. This one's going to be an inequality, much like if we're dealing with, say, a square root, fourth root, sixth root, and so on. X has to be greater than 0. Then it's immediately solved, and we have that as a domain. But there's more than just x right here. We have to take whatever's inside the logarithm and solve that same inequality. So that's really the kind of problems we're going to be seeing coming up next. So definitely the domain is 0 to infinity. Looking at the graph, that's how we would do the range on this one. Doing range is definitely more complicated. We almost always cited a graph and we looked at that. So the range of this function g goes from negative infinity to positive infinity. So that's the conclusion on this one here, folks. Any questions or comments with that quick graph and its domain? Okay, well, after getting through that topic there's a lot more topics we could put together when it comes down to domains. And we can think of example 2 as kind of a review at this point. We're getting to the point where reviewing for the final exam is starting to make a lot of sense right directly in the notes. And if we're trying to find domains of given functions, we might as well look at all the functions we've dealt with so far. Then when we go through this list, we'll look at the new stuff, the logarithmic functions. Maybe just for the sake of tying together this concept, let's do the logarithm to start, and then we'll go through the whole list. Does that sound all right to folks? Okay, let's start it out that way. So this is the process anytime you have a logarithm. The base is not even relevant. This could be base e and its natural log. It could be base 12, base a half, anything valid. Take whatever is here and solve that inequality. So down below, here's the logarithmic functions we have. The moment you see a logarithmic function, you take the input, this is 5x plus 10, and just immediately solve 5x plus 10 must be greater than 0, which is not too bad. We can subtract 10 from both sides, so it's 5x greater than negative 10. Divide by 5, and we have x must be greater than negative 2. So that would be the domain of this logarithmic function. And that means if we were to graph this, honestly, looking at the domain first is a really good idea. It's going to tell us that a vertical asymptote starts right at negative 2, and all of your graph is to the right of it. In other words, domain of this function f is a parenthesis because we have strictly greater than, goes from negative 2 off to positive infinity. So that's how we will handle essentially every single logarithmic function, no matter the base. That could have been base 2, base 12. Let's do it again. This one is another logarithmic function. We take the 8 minus x. It's a natural log, but it doesn't matter. They didn't even have to tell it was a natural log. It could have just been any unspecified logarithm. Do 8 minus x greater than 0. And, well, we can subtract 8. This is a two-step process, but if we want x on the left, that's not a bad thing to take. Divide by negative 1, and now x is greater than positive 8. So that tells us the domain of f is going to be from 8 to infinity on this one as well. So that's the full procedure for logarithms. Yeah. Oh, it absolutely does. Thanks for spotting that. That was my mistake on this one. That should have switched to less than 8, which means right over here, it should have gone negative infinity all the way up to positive 8. Thanks for spotting that one, Justin. That definitely saved the problem on this. I think on this problem, if it was say like a 4-point problem on the final exam, that looks like a -1 point to me. It's definitely an error, but not something that you would lose the whole question on. Other questions on that one there? Okay, related topics to this, again, this section is all about graphing. The domain is extremely important, and we can say, let's put this in orange because it's just a side topic. The moment you see -2 here and the domain starts at -2, that means this function has a vertical asymptote. I'll use V and ASY for vertical asymptote again at x equals -2. That just looks weird. Let me keep it in this color. So there's a vertical asymptote at x equals -2 on this one. And on this one here, we can say the vertical asymptote is at equation x equals +8. So at x equals +8, the graph is now to the left since the domain is all these negative real numbers. Well, that's the entire topic for the logarithmic functions, but we're in kind of review mode like we mentioned for the final exam. So we'll look at the top here and do all the rest of the ones that we encountered throughout the entire course. Any questions at all first with these here? Okay. Well, there is some freebies on these. So these kind of questions can be on the final exam. If you're given a polynomial function like this one's almost a trick question just by the way it's written. You can observe that it has a 0 of -2 if you place that for t. It has another 0 of -3 if you place that for t there. But zeros of the polynomial function have no relevance at all when we are asking about the domain. So only because it's a polynomial, the answer on this, you could write in 2 ways. Well, really three ways. You could just say all real numbers, just ordinary words is fine, and sometimes that's preferable. Or we could write, if they request interval notation, that's the expectation. But even if they write expect interval notation, you're okay to use that symbol there, which represents all real numbers as well. So every single polynomial has this feature, and it doesn't matter how they format it. In factored form, expanded form, the degree is irrelevant. It could have even been a constant function. So watch out for polynomials. And I think this one's also pretty tricky. Anyone see what the domain should be for, say, like a 7th root function? It definitely is. Even this function here, you can plug in anything. But the issue that made it work out, -infinity to +infinity, or all real numbers, is the fact that it's an odd root. So if it was, say, a 3rd root, 5th root, 7th root, and so on, that's the immediate conclusion. But if the root is of the form, say, root 5x plus 10, that implies an index of 2, which is typically not written. But you know what? Let's try it in this time. This is an index of 2, or it could be written in as 5x plus 10. Or anything of this form, nth root 5x plus 10 with n even requires us to solve 5x plus 10. And this is kind of tricky in a way. Anyone recall what should go right here? It has to be positive, right? Because we can't take a root of a negative number in this context for domain. But it could actually hit 0, right? If we put, say, -2 right here, there's no problem whatsoever. In fact, let's calculate it. F at -2, or that f function is the root of 5 times -2 plus 10. That's just -10 plus 10, the root of 0. And that's completely fine. Root of 0 is just 0, since 0 times 0 is still 0. So here, to get the right value, we're just trying to show what x's get us right up to 0, but also stay positive. It has to be greater than or equal to 0 for these kind of problems. And here's the confusion with this. The moment we pick up natural logarithms or any other logarithm, it's not the same, it just feels the same. Logarithms have to have positive answers going inside of it. I mean, we observe that once we graph this thing, there's a vertical asymptote and it's a true barrier. There's nothing out here in the negative region. but it cannot actually obtain zero. If you put -2 inside here and attempt to calculate the logarithm, this is undefined. The calculator might say syntax error, domain error, or anything along those lines. So if it's a logarithmic function, we have to solve in this way, a strict inequality. If it's a root function, we use greater than or equal to 0 to get the full domain. So let's take a look at that one. That's part B here, an even root function. We take 5x plus 10, only because that's the entire quantity inside the square root. Set that greater than or equal to 0, and then just solve. We'll subtract 10, divide by 5. Then we have the conclusion that the domain of this function f starts at -2 and goes to the right forever. So -2 to infinity on this one here. So really pretty much what it's breaking down to is if you can classify the type of function you're looking at, you're pretty much done. You just say what the domain is based off that type of function. For example, odd roots, polynomial functions, those are almost a freebie in a certain sense, but they're also nasty. They become trick questions, especially how they might be written. Watch out for stuff like this. And that leaves one last one, a rational function. Any volunteers for what we should do to solve the domain on this one? Exactly. So because it's rational, we're worried about that again. Notice 5x plus 10 is here everywhere intentionally, just so we can see the difference of what happens based on the function. So we'll set that to 0, like you said. We've done this a couple times, but doesn't hurt to take the steps. Finally, divide by 5. X is equal to -2. And if I zoom out for just a moment, the rational function is kind of similar to the logarithmic functions. Once you find this right here, that's an excluded value from the domain, but that's also the equation of the vertical asymptote. Down here, the domain starts at a numbers larger than -2. So x equals -2 is the equation of the vertical asymptote on that one as well. So coming back up here, we're still not done with the problem, but we can say domain of h on this one goes -infinity up to -2. Then union, take from -2 up to positive infinity. And just to convey that comment we made, I shouldn't box it, that makes it look like the answer, but let's point at it. This is the vertical asymptote. It's even the right equation that you would be expected to write if they're asking what's the vertical asymptote. But when we write the domain, we throw it out. So that's our rundown of all the domain questions you could see on a final exam. The new ones, the ones for Alex, are just the ones on the bottom. So in short, if you have a fraction, it's a rational function, set the denominator to 0 and solve. Even root functions, you set them greater than or equal to 0. Notice the yellow highlighting there. This is kind of tricky when we look at logarithms. Odd roots, polynomials, those are freebies. It's always all real numbers. But compare the logarithmic functions with the even root. Here, we set the input, 5x plus 10, strictly greater than 0 to solve that domain. Well, any questions, folks, with getting through all these? Yeah.
So with the explanation that you have for the odd function, is that n to the square root of 5x plus 10 for that?
Oh, over here? Yeah. Yeah, that's a n right there. And that's meant to be just some even number. Yeah, like 126 or something like that, or even 2. But if it was written as a 2, it's typically like this. We usually negate or neglect the index for an even root square root function. Other questions at the moment? Okay, well, let's take a look next. After getting through all those domains, this was the kind of annoying question in Alex. Again, when you see these kinds of things and they ask you to graph them, they have a process, and it's not a terrible process, but they're kind of making a mountain out of this problem. It's not as bad as it seems, and this is probably how I would personally solve this thing. First thing I'd want to do is determine the domain. It's part of the question, but sometimes the last part of the question is something you might want to do first. So if we sketch the domain or find the domain first, it's going to tell us what the plot should look like. We almost might already kind of know. An x plus 3 means the logarithmic function has moved to the left by 3 different units. So that domain is going to be reflected there. The function is also dragged down by 3 units. It's flipped across the x-axis, and then it's expanded vertically by a factor of 2. So a whole bunch of stuff is going on. Well, that's okay, since what we can do here is, let's just start with domain. We'll take the x plus 3, solve that strictly greater than 0. It deserves highlighting once more because that difference there is definitely tricky. Think strict inequality for logarithms, and you're in good shape. Subtract 3, and x is greater than -3. And now this tells us that the domain of f here goes with a parenthesis from -3 to infinity. That's enough information for us to put this down. Here's our x, or our y and x-axis, said that backwards as I was drawing it. Let's go immediately to -3. And there must be a vertical asymptote right through here. I mentioned this is the problem where we're going to take a look at just solving this one from a calculator. And so what I would do is just start punching these things in. But in order to get this into a calculator, this is not a friendly base. It has a base of 1/2 it there, which is a kind of strange thing to deal with. So we need to make use of the change of base formula one more time that we saw prior to the notes. So let's cite it here. Change of base. It's not the full formula, but it's the formula you would want if you're calculating in a calculator. And I'll write it out like this. Log base b of x is equal to the natural log of x divided by the natural log of your base b. So that's going to allow us to get a really fast xy table. I think we should be able to do it right below here. Here's x, and y is going to be equal to, well, it starts with -2, so let's put that in. But then it's going to be multiplied. It's log 1/2 x plus 3. So let's put x plus 3 up in the numerator here. Natural log. X plus 3 goes there. Then we divide it by the natural logarithm of the base. Our base is 1/2. That's kind of odd to deal with, but that's okay. Base here goes down to here, so the denominator is natural log 1/2. And let me make that a little bit bigger as a table. So all I've done is I'm writing out the function. We applied change of base right here, then -3. So that's the information we have to throw finally into our calculators. Any questions before we give this a try? Okay, and just in case it's useful, let me cite this part of the notes here. This, I believe we did some calculator work in 6.3, I believe. So for your calculator, if you're using a TI-30XA or the TI-30X2S, the buttons you're going to need is pretty much just this natural log button is going to do the job for us. On the TI-30X2S, the natural log is on your far left down over here. Now, if you have your calculator with you today, let me know if you're getting different values or if it's working out. And we'll try to get through this together. So first input we want to put is, well, not -3, that's not even in the domain. How about -2? That might be a good start. That's getting us kind of close to the domain or to the end there. So plugging in a -2 means in your calculator it's probably going to look like this. -2, then natural log. Here I'm putting in -2 plus 3, so I'm just going to put in natural log 1. But you might know natural log 1 is 0. That's a nice shorthand in the calculator already. It's divided by natural log 1/2, then -3. So your calculator, let's see if I can match what it should look like about in Desmos. This is about what it would look like in one just line written that way. So here, -2, natural log 1. So far, the whole answer is 0 because of that natural log 1. We're dividing by natural log 1/2. At this point, I'm just putting it in the calculator just to type this out verbatim. Then finally, -3. So our first result should be -3 entirely. So equals -3, and that's our first point. Well, does that look right to folks? Oh, wrong screen there. Oh, I'm putting this into the calculator. Okay, well, let's try another value. We put in a -3. Let me kind of show more of the graph. I guess we can try, say, -1 and 0, just to get a feel for the rest of the graph. So let's put in -1 next. In your calculator, then, you're typing in -2, natural log. We're placing -1 right here by the red dot. So that's going to be a natural log of 2 altogether. Had a double check there. Divide by natural log 1/2 -3. So plug that into your calculator and you're really good shape. And one thing that's a nice shortcut to some of these calculators is if you put this first line in already, then go to your calculator and hit the second negative sign key. That's going to pull up the last computation you just put in. And then you can scroll around your calculator and just change this one value up here to match with natural log 2 by the red dot. And you should be getting a -1 pretty quickly using that shortcut. Is that what folks have so far? Okay, let me place that in. So we have a -1 here. And you know, it's kind of hard really to see it in Desmos because Desmos is fancy. It's formatting things different. So I'm going to try out a different calculator just to make it look kind of similar to what your calculator is outputting. This one's a graphing calculator. Sorry about that, but at least the input that you see is pretty similar. I don't have a good emulator for any of the other official calculators. Okay, so let's try maybe one more point. This might be enough information to produce the whole graph, but think of this as just extra practice. Yeah, go ahead. Oh, -5. Let me double check it. So let me put it in this calculator. Maybe my mistake was in Desmos. It should start off with this negative sign to start, so -2. That's kind of annoying about even the TI-30X2S. You have to leave with that as your negative sign on the very bottom of your calculator. Then my natural log key is over here. I have putting in a -1. Yeah, that's definitely a natural log 2. Divide by natural log 1 divided by 2. So far it looks like this in your calculator. Then I'm going -3. My output settles at a -1. Are you meaning like parentheses from here to here?
Yeah.
Oh, let's take a look at that. I think we're actually okay in order of operations because this -2, when it multiplies the fraction, it really just multiplies into the numerator. But that's something to definitely double check. Sometimes a little bit more parentheses is not a bad idea. And here's the trick I was mentioning. Instead of retyping in this whole line, on your calculator, this does work. So hit the second negative key down below, and that's a massive time saver. Second negative. Oh, hang on, that's not quite the right one. Let me try again. Try hitting second and then the enter key. That might be the right one that works. Second, enter. Yeah, that pulls up the prior calculation. Then over here, let's insert a parenthesis. And then way over here, a second parenthesis as well. So with the extra parentheses, we should still be getting that same answer. But that's definitely a good call with these calculators. Sometimes more parentheses is just good practice, just to be sure we got it in the exact way we expect it to be getting in. Other questions so far? Did you find the issue with that -1?
Yeah.
Awesome.
Put a negative on the very beginning too.
Oh, I gotcha. Yeah.
I can catch it on the put X is -2, apparently it's
Mhm.
same. And positive 2 and negative 2.
Oh, they matched.
And,
Yeah. That's kind of impressive, actually. Yeah. Well, other questions at the moment? Okay, well, we've got 2 points. Let's maybe try one more. Let's maybe put in, say, 0 and see what happens there. So if I plug in a 0, I'm putting on paper first what would be going into the calculator. So right by the red dot, that's where your 0 is going. So it's going to be a negative 2, natural log of 3, divided by natural log of 1/2, and then minus 3 on that thing. Then you could type that into the calculator, or I encourage you to give this function a try again. Hit the second key on the very upper left, the enter key on the very upper right, and we're just going to make one quick change. It's natural log 3 in the numerator. So that just flips to a 3 right here, saving us a lot of time, like about a minute possibly, but in the end of the day, a couple of these minutes would add up. This one's not nice, and if you're putting this into ALEKS, I would say put in some extra decimal places. That way they're not going to complain too bad. 0.16993 is probably what I'd enter. 0.16993. That one was definitely not a friendly value, but that's okay. We can still plot all these. And so with what's highlighted so far, those would be the ordered pairs that I would plot. Any questions then, folks, before we go to sketch this full graph? Okay, so now we're just plotting points. At -2, we take on a value of -3. So that's our first point here. At -1, we're at -1. Then at 0, we're at 0.16993. So about here, pretty close to 0. That looks like our function is doing something like this. With just the 3 points that we produced, we know it has to be attracted to this vertical asymptote here. And so the function had to go down and get closer and closer to that vertical asymptote. Logarithms are also increasing functions, so we're expecting it to go up. Even though there's a negative right here, there was an extra reflection right on the base being less than 1, but bigger than 0. So that caused a separate reflection that got corrected with a -2 here as well. So that's finally our full graph. If you're doing this in, say, ALEKS, and you're just suspicious about your graph, you could always put it into Desmos to just double check if it looks right based on your work there. The reason I did this one and kind of made a big deal out of the calculator is, I mean, that's a decent way to do this topic. And also, I think ALEKS is just trying to get us to do a lot of extra work on a problem that shouldn't be so bad. I encourage you to just hit a calculator if you see a big function like this. Well, any other questions, folks, on getting through these topics? Okay, I would say the bigger takeaway on this section, it's a pretty short section, same in ALEKS, it's like 5 topics, it's really easy to get through. Big takeaways is probably this, example 2. The domain is really, really important. So is the range, and I think I forgot the range on example 3. We have the domain here. Let's just finish out range as well. Sorry for that last topic. It's not so bad. The extent of the y-coordinates is from negative to positive infinity. And so range f is from negative positive infinity like that. Okay, well, I think we're ready to take a look at section 6.4. We're not trying to complete it, just get into a good position so when we come back from the break, we'll know just about what's going on. Once I close these. Okay, so here's section 6.5. After this section's done, there's just 2 more left for the course. So congratulations again, we're just about there. Let me show you about kind of how these notes are organized. We just did a problem where we used heavy use of the calculator. And now I put a comma here. These problems can be done quickly with the calculator, but I encourage you to try these ones out by hand. The reason for that is we're going to practice how these logarithms work. And as we get down, we're going to see what properties are going to help us out. There's certain problems where, like say A and B, you would never want to reach for a calculator. The answer is kind of just staring at us. For example, the answer to part A here is just 5. After we get through all that, we'll do a couple more problems like this where it's just by hand. And the reason we're doing everything by hand, even though a calculator can just rip right through them, is because the real problems we're interested in go like this. We want to expand logarithmic expressions that involve variables. The calculators won't help us here, and this turns out to be an extremely important problem. If you know you're going on to calculus, this process is important for differentiation and integration. So it becomes something that suddenly in calculus, if we're not too fluent on, these are terribly difficult looking problems when they really shouldn't have been. Then we'll reverse that whole process. We'll take expanded logarithms and try to compact them into just one logarithm. The reason for doing that is we'll also be solving equations, and this is very often a necessary step to solve equations involving logarithms. We need to condense them as much as possible. So for all this work, the calculator is of very, very little help. It's for that reason, I'm going to do this set of topics just by hand to help us out when we get to the harder topics. No harm though if you double check your answers with a calculator. It's good to be fluent with that device as well. Any questions, folks, before we give these a start? Okay, so it's just a set of some strange looking logarithms. It says here, evaluate each logarithm. Evaluate means we're just going to put a number on these. But sometimes it's not a bad idea to start off by doing this. Put a symbol on it first. Let's call this maybe x. So I have a log base 3 of 1/81 equals x. Determining x, you might know what it is already. If you do, don't hesitate to call it out. That'd be terrific. If we're not sure what it is, that's the great way or a great purpose of the exponential form of the equation. So let's go to exponential form. Base is 3, and I'm copying that strategy again that I messed up at the start of class. Good idea to keep your base here at the same side of the equation where it started on, because now we can see a little bit easier, at least I can, that x goes in this location. And 1/81 goes into this location. So we changed the equation from a logarithmic one to an exponential one. And it doesn't look like that's helped us, but it really has. This equation here is much, much easier to solve in certain sense, depending on how you look at it. We can call this 3 to the power of x. And 1/81, that turns out to be 3 to the power 4. So that's a perfect fourth power. 3 by 3 is 9, by 3 is 27, and by 3 again is 81 altogether. Now, if I have a base here in the numerator, exactly, and a base here in the denominator, you bring it up and you found the answer, -4, like you said. Up here, if you saw it, -4 is the power you put on 3 to get 1/81. You could have been done right at that step. Or you could throw it into a calculator and get the same result. Again, think of this as practice for what we're going to do at the very bottom of the notes. Last step, 3 to the x equals 3 to the power of -4. And this is an equation where the base is the same. Whenever the bases are the same, the exponents must also be the same. So we have an immediate conclusion. We'll say, therefore, x equals -4. It's maybe not the best answer in all honesty. It's good to tie together the original question. Log base 3 of 1/81 is -4 on this one. And again, if you're doing these on ALEKS, no harm double checking in with a calculator either. Any questions with that one there, folks? Okay, so we did it. We've solved a logarithmic equation in a certain sense. We put in x, we made an equation and solved for that x. But really, it was just an evaluation of that logarithmic function. Now, this one here, we could try it again, but this one's kind of tricky. Anyone see what the trick is on part B? Exactly. The moment you see a negative there, we have a big problem. We can go back to our prior section, which says domains of these logarithmic functions involve the input to be positive. Or if we looked at this one, log base 5 of x requires x to be positive. On a graph, you can never put in negative numbers. But all of this kind of looks different until you get to, say, right over here. We just have to recall that there's a graph and we can't even put a negative on that number there. Question over here. Well, that's going to the land of complex numbers, and in complex arithmetic, you can take a logarithm of any number whatsoever. Yeah, so you're getting weird, interesting results. And if you're curious about that kind of stuff, you could take a look at Introduction to Complex Variables and later on Complex Analysis. These functions as real number functions extend to the entire complex plane, and so you can really calculate them. But those answers are not real numbers. And so for this one, we'll say here the expression is undefined, since we haven't done that pretty difficult work of defining a complex based logarithm like that. So here, pretty much what I would say is, since the domain is from 0 to infinity of this particular logarithm, natural log of -3 is undefined. Deserves an exclamation mark. That's really important for us because when we're doing some equation solving, we can pick up extraneous solutions that are not even in the domain of the original function. So we have to test solutions. Occasionally you might test out this natural log -3, and you have to know, oh, that's not even a real number. So it cannot possibly be a real number solution to that equation. So that's two strange problems so far. Part A is the normal kind of question. Part B is just a reminder that there's important domain considerations. And part C is kind of like part B. If you see natural log, it's log to the base of e. If you see just log, anyone recall what logarithm that one is really? Exactly, that one's to base 10. So log base 10 of 1,000. Any volunteers for what that might be? It wouldn't be 100, but you're not on the wrong track on there. We have to think about the powers of 10. So the output to this is going to be the exponent that you have to put on the base, which is 10, in order to get 1,000. If we're not sure what it should be, this strategy up above still definitely works. We can throw in an x as just a temporary placeholder, rewrite this whole equation just to exhibit the base as log to base 10 is what we're really dealing with, of 1,000 equals x. Now let's convert this to exponential form. I'll keep the base on the same side like before. This output of x becomes the input to our function. And the input to the logarithm becomes the output to 10 power x, the exponential function. Now we're at pretty much this stage on part A. The 1/81 is playing the same role as the 1,000 there. And what we want to do is try to factor this in a certain way so a base 10 emerges once again. For example, 81 factored as 3 power 4, and then we just brought it up and found the answer. So the next step we can say 10 to the power of x is equal to 1,000, but 1,000 can be rewritten as 10 to the power 3 now. At this stage, we have an answer. The only way that this equation is correct is if the exponents match. So here to here, we can say next, x equals 3. And our conclusion is, therefore, log, let me try again with the letter O, log of 1,000 is now 3. 3 is the exponent that you have to put on 10 in order to output 1,000, is what that equation over here is now finally saying. That makes sense to folks so far on these? Okay, well, let's go off to the next topic then. Think of these problems here, kind of a warm-up as well. And what we want to get to next is some interesting properties of logarithms. And the first important properties really come from the fact that we're dealing with an inverse function. Let me scroll to this part right here. This definition is when we were in chapter 3. This is our first look at what we mean by inverse function. If we have f is 1-to-1, we'll denote f inverse to mean the inverse function. And it gives you two equations immediately. We're going to turn those equations into properties of logarithms. In essence, if you compose f of f inverse, there's a cancellation. Whatever f inverse has done to x, f undoes it, and you just get x. But that x has to be in the domain of the inverse function. The inverse is the first thing that's evaluated. Over here, if you change the composition and do f inverse of f, well, then this x has to be in the domain of f, but then you output just an x. Then, if we put in our formulas, we can change these domains. The domain of f inverse is from 0 to infinity, like we've been looking at in the prior section. The domain of f, which is the exponential function, is from negative infinity to infinity. So we are changing the domains to match the fact we're using b to the x as our original function, and log base b to the x down here as the inverse function. So those are the appropriate domains and ranges. These are still the right equations, but if we plug in the b to the x and log base b to the x, here's what it looks like. These are the official properties right here. And they're properties about cancellation, which means we can use these to great advantage when we're solving equations. If we need to eliminate a logarithm, for example, that's no trouble. We just use a base b on both sides of the equations. I'll undo this cancellation, but this is visually what's happening. B to the power of log base b. If those bases b match, you get just x out. And that's because we're dealing with inverse functions. It's really just this right here that we're dealing with. Oh, sorry about that. Let me get rid of that. Likewise, down below, if you need to get rid of an exponential function, you take log base b of it, cancels this way, and you get just x back. So we have a way to eliminate a logarithm or an exponential in an equation, which means we have lots of equation solving tools now, just all of a sudden. So these two are the properties of logarithms. Coming from inverse function, let's say inverse function facts. So let's use this information here and do another set of really, really fast problems. For example, if you see part A here, and it's asking you to evaluate e to the power of natural log 5. Any volunteers for what the answer should be? It's got to be 5, exactly. So visually, it's a cancellation. The reason that works is we're really looking at e. We have to know if you see natural log, it's log base e of 5. And so the cancellation is really kind of going this way. The whole answer is 5 altogether. Right over here, the goal is to just see this. E with natural log involves cancellation. Your answer is 5 immediately. But we have to be careful because keep in mind there is domain and range issues on this. We had the exponential first, and the exponential first only works if you're dealing with positive numbers right here. If you do the logarithm first and do b to the x, that one's nice. Nothing ever goes wrong. You'll get x for any real number whatsoever. But watch out for this one. It comes from the fact that the domain of a logarithm is 0 to infinity, unless there's something else in the input. So this right here is something to watch out for on these properties. This one's not as bad, but it's just not in a good format. We could fix this and say it's log base 2 of, not 16, we need to put a power on 2 instead. 16 is 2 power 4. And at this stage, we're pretty much done. Any volunteers for the answer on that one? Exactly, we'll cancel here to here. Well, let me use that same pen. Log base 2 cancels with 2 to the power, and we get just the power itself. 4 comes right out. Then we have to be very careful, right? This one looks like it should work. 10 and log here with no specification does indicate log base 10, but this is where this domain condition goes wrong. We know log base -4 itself is undefined. That means the whole thing is undefined, and we don't have any property on this one. The only answer we can write is undefined. But then again, if you have a really powerful calculator and you're interested in complex numbers, you can define a negative logarithm. It just takes a little bit extra work beyond what we're doing in this class. Any questions so far, folks, with A through C? Okay, yeah, go ahead.
So for the second example,
Yeah,
is it two that we're canceling out? For B?
it is. It's the log base 2 as a function, and it's the base of 2 here as well. That's all canceling out.
Okay. And then for the first one, it was the log base E and the E that we're canceling, just getting by itself.
Exactly, yeah. I wrote it out this way a second time just to show how it's really working in the properties up here. The actual B is E itself. Other questions at the moment? Okay, let's try out part D next. Part D looks suspicious, definitely, after dealing with, say, part C. But recall, we're in this condition, property number 2 right here. It's going to be, or hang on, let me take another look at that. No, we're in property number 1. We're looking at an exponential, then a logarithm of a number. We see a negative sign, but this one is defined. 3 power negative 1 is a third. It's a positive number. So the cancellation this time goes 4, which is an exponential function to a power, cancels with log base 4, its inverse function. The whole output is just 3 power negative 1. Or you could call that 1/3 if you like. I'm not too picky. You could leave it with the negative exponent, and that would be just fine. So that's what happens with those kind of problems so far. And really, there's not a whole lot of additional examples you could write about this kind of stuff. Since the properties are about cancellation, things are lined up right, then you just get the outputs that we're seeing here. But the only one to really watch out for was this one right here. We couldn't put a real honest negative number inside a logarithm, and so that property broke down. Well, that's our major properties at the moment. And if we turn further down into the notes, there is a whole heck of a lot more. There's the product rule, quotient rule, power rule, and we can study these pretty carefully. What's going on with every one of these rules is a logarithm itself is just an exponent. And we look at that from the point of view of a logarithmic equation could be written in exponential form. Then every single property about exponents that we know, love, and use all the time can now be translated into a property about logarithms. They're just exponents themselves. So the exponent law for the product rule says if you multiply bases together, your exponents have to add up. Keep in mind, logarithms are exponents, and so when we say exponents are adding up, the x plus y here is this property. The logarithm of 2 things multiplying together is the sum of those individual logarithms of x and y. That's a fantastic property, and that has a lot of ramifications. One of the reasons we like logarithms is it compacts things or expands things whenever we're looking at a multiplication. Likewise, if there's a product rule, there's a quotient rule. The quotient rule involves a negative sign right here, which gives us a negative in the logarithmic equation. So if you're multiplying logarithms, or excuse me, if you're multiplying values inside your logarithms, just add the logarithms. If you're taking log base b of x divided by y, subtract log base b of x from log, just take log base b of x and subtract log base b of y. And this power rule has tons of properties as well. Oh, I'm not sure if I wrote down that power rule. B of the x to the power of p, let me actually pen that in. Sorry, that just got left off. Is b to the power of x times p. That one turns into a multiplication formula. And the way the multiplication formula goes in the logarithm realm is, if you have a power on your logarithm and it's inconvenient, no trouble, you multiply the logarithm by that power and just completely peel it off x itself. So that's our logarithmic property right down below. To the right are just fast examples. Log of 8 times 2 can be rewritten in this way if we needed to. I'm not sure why we would do that, but that's just an example of how it would work. If you're taking 8 divided by 2, you're just taking log base 2 of 8 minus log base 2 of 2. This one is going to be a 1. And if you have a power here that is inconvenient for any reason, you can get rid of it. Just put it down as a coefficient, making it multiply. So those are our new properties. And I thought maybe before we go off to a break, let's do just this part right here. I don't want to get too far in these notes because we have to come back after the break and re-go through this information. So let's do this one and we'll do some more as a warm-up when we come back Tuesday. Does that sound all right to everyone? Okay, we'll end a little bit early today, but I think that's appropriate. We've been working hard and we're in a really great position to end the course with enough review time. So here's our first property we're going to take a look at. This is, again, another one of those problems where you can just throw it into the calculator and get an answer. But I encourage you, when you see these in ALEKS, practice doing it numerically by hand, because the problems are going to eventually look like this, and we really have to do it by hand. It's easier to practice right now when things are familiar and nice to work with. If we throw it into a calculator, we're robbing ourselves of that extra practice. Well, first thing to observe is I cannot use the quotient rule property. I'm prevented this time. Yeah. Exactly. That's the trouble with this one. Exactly. So you're saying we need to get rid of this first, right? Absolutely. That's really terrible about this problem is if you have a coefficient here, this property is prevented. Observe there is a coefficient of 1 here, a coefficient of 1 here, or -1 really, if you bring in the sign. So anything like this, good eye again, it has to be eliminated as a very, very first step. Let's make a huge deal out of that right here. Let's say first, actually, let's say we must. Must is a very, very strong word here, and I think that's appropriate. We must eliminate's not the right word. Let's say relocate this coefficient as a first step. So before we do anything at all, product rule or quotient rule on these logarithms, eliminate your coefficients or relocate them is, again, the better statement. Like Michael was saying, you can take that 2 that was there, write it as log base 3 of 4, now to the power of 2, minus log base 3 of 48. So that's where we're going to get a 16 altogether. And looking up at the power rule, here's what we did. We took a power here and just relocated it into an exponent where we see 4 squared. Does that make sense to folks on that first step there? Okay, after dealing with that coefficient, it's not so bad. Let's take it and write it as log base 3 of 16, just to simplify a little bit more, minus log base 3 of 48. And now finally, when we see this negative sign here, we're in business. We can use the quotient rule on this problem. The moment there's a difference of logarithms, we'll have the logarithms of the quotient of the outputs. So this turns into log to the same base of 3 division here, just to tie the negative sign that we saw. 16 is above, 48 is below, and that actually reduces. This problem simplifies in a really big way. So 16 goes into 48 3 times. This is log base 3 of 1/3. Anyone see what the answer would be at that stage? It's kind of tricky to see, but we can take one important step. It's -1, good call. If you didn't see it at this stage, take this one additional step. But if you do see it, you can just put -1 right now, and that's a valid answer. But the extra step would be log base 3. We're going over here and writing this as base 3 in the numerator. But that means the new exponent is -1. And now we have a logarithm to the base of 3 with the input of an exponential function to base 3. These are completely inverse functions. And so they have eliminated each other, leaving just that -1. So this whole thing, 2 log base 3 4 minus log base 3 48, is just a new way to write -1 in this problem. Kind of nice. And if you put that in your calculator, you'd have to use change of base twice, but you can do a fast check and show that that is really the right answer we're expecting. It's possibly just as fast doing it by hand once we get fluent with these properties up here. Well, any questions at all, folks, on that example there? Okay, well, when we come back on Tuesday, wow, it's going to be a while, Tuesday, November the 21st, this is where we're going to be at. We'll review some of these problems. I might have just an extra document where we just do a quick warm up of everything that's gone down so far. Then we'll come back to these notes and finish them off. We're going to be in really great shape so that when we come back on this week here, we'll definitely have some review time for the final exam. Well, any less questions or comments, folks, before we head off to the break? Okay, well, have an excellent restful holiday, folks. Try not to work too hard, stay safe. And again, if you do have questions, if you're working on math, don't hesitate to email. I'll be checking usually in the morning, but you can email at any time. That's a pretty impressive calculator, I have to say, Michael. Most calculators can't handle logarithms of negative numbers. I think even Desmos, if you try to put something in, like natural log, -5, doesn't want to deal with it at all. And that's a pretty powerful calculator on Desmos. What was that? Yeah, it looks like that one's pretty as good as a computer, really. Computer algebra system, yeah. Yeah, those were pretty cool things. Any questions?
Yes, so I think over the break, we're gonna have quite a bit of time.
Mhm.
My concern is that I'm going to forget everything, because, that's how it goes. Once
Well,
you're
I
not
have
doing-
some good news about that. If you have extra time on the break, I will be posting some review material there. Sample final exams, sample final exam problems and that kind of stuff.
Okay, because I know that there's some stuff that we haven't quite finished yet. I mean, we're obviously getting there.
Mhm.
It was just like all of the other materials, so I didn't know if like there was like a place on Alex that we could go.
You know,
Or like
there isn't
even-
at the moment, but I could create a huge a review exam if you'd like.
Yeah.
Awesome, let me put that down.
That would be extremely helpful.
It means you're doing Alex problems, but I mean, you get instant feedback. That's pretty helpful for
Mhm.
sure.
Yeah, especially over the weekend or over, I guess, the next week.
Gotcha. So I'm gonna figure out how to do that. I've done it before, but it's been years since I've used Alex.
Okay.
So we want an Alex exam review. And I'll email you once I get that all set up so that you can find it. It'll probably be in your assignments list.
Okay, sweet. Okay, thank you.
Yep,
Yeah,
you
I was
bet.
gonna say like, even like the homework, being able to finish out the homework would be nice, but.
I am gonna unlock all the sections too, so you could absolutely finish out all the homework.
Okay, I think that would actually be extremely helpful and then also gives a little bit of a boost.
Absolutely, yeah.
Thank you.
Yep, you bet.